Okay, go ahead.
Okay. Hello, everyone. I'm Elliot, and I'm going to be continuing my talk from last time. And it's kind of convenient that this is going to be the last talk of the semester because I'm hoping to be able to tie a nice little bow on the main Kapustin-Witten argument and the relationship between geometric Langlands and physics. So right here we see we're going to be talking about branes today, and we have the Hitch and moduli space surfing over a Dbrain over its Langlands dual. It's a little bit of a pictorial representation of the stuff that's going on behind the scenes. So let's get started, okay? So just as a little summary of what I'm talking about, what I'm going to be saying today, I'll start with a review of what I did last week and the categorical formulation of geometric Langlands that Stephen talked about, I don't know, 3 weeks ago now. And then I'm going to move on to talk about branes, defining what they are and how to deal with them, and then homological mirror symmetry as a relation to that, which is the categorical formulation of mirror symmetry. And it's going to relate very nicely to that of the geometric Langlands. And then to actually make this correspondence explicit, I'm going to introduce line operators, and then the eigenbranes of these guys is going to correspond very nicely with the eigensheaves of geometric Langlands. And this is going to basically put a bow on this whole last 4 or 5 weeks that we've been talking about this stuff. So last week, what did I talk about? So here's basically the theme. We started from S duality, where we noticed that the Langlands dual showed up oddly in physics. And we're trying to go from basically the physics notion of S duality to the mathematical one and see if it gives us any new perspectives on the mathematical notion. So the way we did that, we started with an n=4 supersymmetric Yang-Mills theory in 4 dimensions. We compactified 2 dimensions, and then this resulted in giving us a sigma model with the target space of the moduli space of Higgs bundles, or the Hitch and moduli space. And we noted that this had basically the non-abelian Hodge correspondence on it, where basically if we looked at this moduli space from 2 different perspectives, one of them would give us the space of flat bundles, while the other would give us essentially the cotangent space to the space of all the moduli space of all bundles. And these are exactly the structures that we wanted from geometric Langlands, and that's very nice, and we're going to be taking advantage of that today. Finally, we introduced basically the Hitchin fibration on this guy, and noticed that it exhibited T-duality, where the Hitchin moduli space here and its Langlands dual are fibered over the same base. And in fact, the relationship between the fibers, they're both Lagrangian tori and they're dual tori to each other. And this is the picture of SYZ mirror symmetry. And what we're going to do today is we're going to take advantage of that mirror symmetry and reframe it in terms of a homological version, a categorical version, and use this to finally relate to the categorical version of geometric Langlands. Okay? So let's review a little bit about what the categorical geometric Langlands is. So there's 2 sides. There's the arithmetic side and the automorphic side. So the classical version of geometric Langlands, we start with a flat GL bundle, a flat bundle in the Langlands dual group on the arithmetic side. And we want this to correspond exactly to to a Hecke eigensheaf on the moduli space of all G bundles. Now, Stephen talked about this in length, but basically we can convert these are naturally elements of some sort of category. So for example, for a flat GL bundle, we can consider this as a point over the space of local systems of the Langlands dual group. And that point we can consider as just a skyscraper sheaf. And that skyscraper sheaf is naturally an O module, a module over basically the structure sheaf over this space here. So this naturally sits inside the category of O modules on local systems. On the automorphic side, we have a Hecke eigensheaf, and we can naturally think of that as a D module. That's a module of the sheaf of differential operators, basically some structure that can be differentiated, kind of. So this, again, naturally sits in the derived category of D modules. Now, we have basically the classical geometric Langlands is that these very specific objects of these sheaves correspond to one another. And what would be great, like the best, is if actually this came from an entire equivalence of these categories with each other. This is the daydream, is that we have some equivalence mapping these whole categories to each other that sends the desired objects of this guy to desired objects of this guy. Why do we care so much about that? Well, it's interesting because it gives us essentially a spectral decomposition of the category of D modules. So the skyscraper sheaves over given points gives us a sort of decomposition of the O modules of the space of local systems. So if we decompose the space of local systems like that, and then pull it over here to this guy, that will correspond to basically a decomposition of any given T module into a bunch of Hecke eigensheaves. So like a spectral decomposition and that sort of thing. So this is why a full equivalence of this sort of category would be so great, because it'd give us this interpretation. Now, to get started on the physics stuff today, let's talk a little bit about, these topological quantum field theories, TQFTs. So from a certain point of view, you can think of a quantum field theory as assigning essentially a number to some Riemannian n manifold with some boundary conditions, right? Now, the topological quantum field theory, we're imposing that the local data doesn't matter at all. The local data in this case being the metric. Now, if the local data doesn't matter, then what that effectively means is that the only thing that does matter are the boundary conditions. Because effectively, you can take the boundary conditions and just extend the solutions of them out over the whole manifold, because it doesn't matter what the local stuff is. So the idea of topological quantum field theory is just let's axiomatize this by kind of cutting out the middleman and just basically define the topological quantum field theory by the boundary conditions. So this is in the usual sort of axiomatic definition given by Atiyah. We have our n manifold, our whole closed n manifold we associate to a number. That's the partition function. And then for any given boundary of that, an n-1 manifold, we associate a vector space, which is kind of the space of states. We can actually do one step further. We can do one better than that. We can consider the boundary conditions for the set of boundary conditions. Right? So let's do this little doodle in the two-dimensional case. So we have this two-dimensional manifold with a one-dimensional boundary. And suppose that this boundary had two components with different boundary conditions on each. And then there was a sort of place where it jumped between them. So at this jump, what this corresponds to is basically it has to send the information from one boundary condition to the other. So the states on this one get mapped to states on this guy. So it's like a morphism from the category of these boundary conditions to these guys. We can glue this together into a full category of boundary conditions because of essentially the trick where we can compose these sorts of morphisms together. If we consider like a boundary condition B to B prime to B double prime, if we look at it from the outside perspective, this is equivalent to a single morphism from B to B double prime, right? So this is a composition of morphisms. Basically, the idea is boundary conditions form a category. Now, the idea with extended, we can do this whole operation a few more times, as many times as we want actually, and get what we call an extended TQFT. So what if we actually had a boundary condition of these boundary conditions of boundary conditions? So this would correspond instead to an n-3 manifold, and it'd be a category whose objects are categories and morphisms are endomorphisms of those categories themselves. That's called a two category. And we can do this over and over and over again. And basically this is the notion of extended TQFT is defining a topological quantum field theory as basically this tower of higher categories. But this is important for the full treatment of the subject, but for this talk, we're only going to be essentially using the 2D case. So we're interested in categories of boundary conditions. So what do these boundary conditions look like? Well, this is the notion of a Dbrain. So we're in a two-dimensional case. So what we're considering is essentially we have a two-dimensional manifold and we're considering a sigma model on this. So it maps to a target space X. And this is a two-dimensional, it's actually conformal field theory. And there's a very useful sort of different point of view we can take on these things where we can consider a field theory on this two manifold instead as strings. So we consider the two manifold as basically the world sheet traced out by a string as it propagates through space-time. And the space-time it's propagating on is the target space X. So So let's impose boundary conditions, as we're actually going to impose durationally boundary conditions. And we're going to impose the values of the fields at the boundary of this 2D field theory. And the way we're going to do that is we're going to specify a certain submanifold of our target space. And we're going to just say that on this boundary, all of the fields have to lie somewhere on the submanifold. And we're also going to associate this with a sort of a vector bundle, or more generally a sheaf. That's called the Chan-Payton sheaf, Chan-Payton factor of this guy. But basically these sets of data together, a submanifold and a vector bundle on it, if we also demand that it preserves conformal invariance, then by imposing these theories, these boundary conditions on our theory, we get a new string theory. And then what we call these Dbrains for durationally branes, because durationally boundary conditions, brane for membrane, because it's a membrane, see? And let's take an example. So we have our whole two-dimensional space here with these couple of boundaries, and then basically we're considering strings on this correspond to what's called open strings. So basically these are strings that map from one boundary to the other, one end of the boundary to the other, and in the target space, these are like strings that kind of go between the two different boundary conditions, right? That's this guy here. So next step is to impose supersymmetry. So how do we manifest supersymmetry? Well, we have some supersymmetry operator Q that's nilpotent, so it squares to 0. And we're demanding that this is a symmetry of our system, which means that basically the branes that we have are going to need them to vanish under action by Q. Moreover, since it's a symmetry, anything that comes from the action of Q, we demand to be trivial. So after we do a topological twist to our theory, then this isn't really a supersymmetry operator anymore, but the same sort of notion applies. And we can think of this instead as a BRST operator. And basically what I'm saying here, what I'm claiming here is that the space of physical things that we care about is the cohomology of this operator, the BRST cohomology. Now, let's look at this from a different perspective instead. So we can think about the cohomology, but instead we can actually think about this as the actual chain complex associated to it instead. So we consider, instead of the cohomology, we consider chain complex modulo what's called quasi-isomorphism, basically isomorphisms of the chain complex that preserve cohomology groups. And this is a very well-known notion in category theory. This gives the notion of the derived category of these branes. Remember, these branes are an element of a category that was on the last slide. And by imposing supersymmetry, it basically says, by imposing BRST invariance, we're basically passing to the derived category of that. Now, we need a little bit more stuff about the notion of these strings that we're gonna use later. So again, the notion of open strings. So let's look at, basically recall what we had as our functor, a point operator put on the boundary acts as a morphism from the branes here to from the brane here to a different brane. But again, let's take a different point of view. Let's cut out a little section around this operator and integrate out all the degrees of freedom around this section. When we do that, we're basically cutting this out and pulling it to infinity over here. You can think of it like that, and then we have this operator becomes a state in the asymptotics here. But basically, the space of strings on this guy here corresponds to the space of open strings stretching between the brane B and the brane B prime. So more explicitly, this operator O describes a homomorphism in the category of branes from B to B prime. And what I'm saying here is that this is equivalent, this is a vector space, and it's equivalent to essentially the Hilbert space of open strings mapping between these guys. That is, any morphism in our category of branes corresponds to some open string stretching between two branes, a state of open string stretching between the two branes. Okay, so let's look at some examples of Dbrains. Let's start with The next letter to consider is B-branes. So again, set up, we have a 2D sigma model mapping from a Riemann surface with boundary to a Calabi-Yau manifold. And what we're going to do is we're going to impose a type of topological twist called the B-twist. And the net action of this is roughly, it sends the supersymmetry operator to just the del bar operator on X, which means that we want to consider BRST invariant states. So that corresponds to states with del bar equals 0, as in essentially branes that are holomorphic. And what I mean by holomorphic, I mean that they correspond to complex submanifolds, and their Chan-Payton factor, their Chan-Payton bundle has to be a holomorphic vector bundle sitting on the submanifold. Now, we need to turn this into a nice category, and the way to do that is with coherent sheaves. So just a reminder, so holomorphic vector bundles, you can think of those as sheaves that are finitely generated as O of X modules, the structure sheaf on X, the sheaf of holomorphic functions on X, right? The issue is, to do what we need to do later, we need this category to be abelian. But the category of vector, what that means is that it's closed under the operation of taking kernels and co-kernels. Trouble is, the category of vector bundles is not abelian, because basically, though pointwise the kernel of a map from a vector space to another vector space is still a vector space, the dimension of that can jump, which means that we don't have a well-defined dimension on our kernel of a map between vector bundles. So as an example, for completeness sake, so let's imagine our bases are 2, and let's just have a trivial line bundle over it. And we're considering a map from that to itself, where we just take the line bundle factor and just multiply it by, say, the function x. So this has trivial kernel whenever x isn't 0, but when x is 0, the kernel is the whole line, right? So we get, instead of getting a vector bundle over the whole surface, the kernel of this gives us a vector bundle over a submanifold. And this is really easy to generalize to basically any variety defined by the zero set of some function. If we just multiply by that function, that gives us a map between a vector bundle and itself, and the kernel of that map is the restriction of the vector bundle to that submanifold. So basically what we want to consider is essentially the abelianization of the category of vector bundles. That is roughly the smallest sheaf that contains all the kernels and co-kernels in vector bundles. The smallest abelian sheaf containing the sheaf of vector bundles. And because of this construction here, this basically naturally holds all of the vector bundles on submanifolds. And in fact, just from the vector bundles on submanifolds and vector bundles on the whole manifolds, if you add them together the right way, you can get any coherent sheaf like that. Basically, the point of all of this is that the natural category that B-branes sit in, the natural abelian category, is the category of coherent sheaves. And more explicitly, the derived category, because again, imposing BRST symmetry. That's what that does. Okay, cool. Let's look at the other side of the coin, which are A-branes. These are maybe a little bit harder to define. So while B-branes are defined with respect to the complex structure on X, these are corresponding to the A model, right? So they correspond to the symplectic structure on X. So the pair is a submanifold, like any D-brane, the pair is a submanifold Y and some vector bundle of connection. And to impose the symplectic structure on X, the way that this manifests is by saying that Y is actually a coisotropic submanifold. What that means is the symplectic form on X, when restricted to the normal of the tangent bundle of Y, is 0. The concrete application of this is that basically the dimension of Y has to always be greater than half the dimension of X. Now, this is a little bit unfamiliar because, like, when people talk about A-branes, almost always they're talking about the Lagrangian case, which is the case that physically is the most obvious. This is essentially the Lagrangian submanifolds are those where the dimension of Y is exactly equal to half the dimension of X. And in this case, from physical considerations, you can show that the associated connection on the Chan-Payton bundle has to be flat. So what are morphisms between A-branes then? Well, these are open string states. So basically we have our two-dimensional submanifold with two components of the boundary, one of which corresponds to one A-brane. So it has to lie on essentially one Lagrangian submanifold, while the other has to lie on the other Lagrangian submanifold. And for this to work out nicely, what we need is that as we go to infinity, that these, for this to all essentially be continuous, that these have to end up at the same point. So on this end, it goes to P2, and this end, it goes to P1. And this boundary up here, the top boundary, has to basically live in the first Lagrangian submanifold. This other boundary lives in the other Lagrangian submanifold. And the map that sends this over here, it sends this Riemannian surface, it has to send it to basically what's a J holomorphic curve, basically something that satisfies the Cauchy-Riemann equations. So what that means is the space of open string states is naturally considered as essentially complexes of points in the intersection of the two Lagrangian submanifolds. Remember, these are both half-dimensional, so these generically intersect at single points, or that's a finite number of points. Anyway, so it's a complex of these points together, and the differential of this complex is counting the number of J holomorphic curves where one end of it lies in one manifold and the other end lies in the other manifold. And this is exactly the notion of, it's called Lagrangian intersection Floer homology. So putting it all together, this is what's called the Fukaya category, basically the notion of the objects of the Fukaya category are Lagrangian submanifolds, and their morphisms are given by this, like this Floer homology complex somehow. So what is the full category of A-branes? Well, it's kind of hard. This is why I said that the B-brane case was maybe easier, because the A-branes is, well, it contains the derived Fukaya category, that's for sure. But we also need to include basically all of these coisotropic things. And like the conditions about what coisotropic things to include and what you need for it to have mirror symmetry is actually, it's a really subtle problem. And I put extended in quotes here because there's some ambiguity in the literature, I'm pretty sure, about how to define the Fukaya category. So some people take it as essentially this construction that I was doing up here, just with Lagrangian submanifolds. Well, other people take it as the thing which you need to get mirror symmetry to be true. That is, you include all these coisotropic manifolds and stuff. I'm just going to call this the Fukaya category. So basically the category of A-branes is the derived Fukaya category. Cool. Now we can finally have homological mirror symmetry. So the statement is just that essentially the B model over here sends to the A model over here. That is, we have an equivalence of categories between the category of B-branes, which is coherent sheaves, derived category of coherent sheaves, and the category of A-branes, the derived Fukaya category, where basically every B-brane has a dual A-brane. So let's see how this plays out in the one situation of mirror symmetry that we are familiar with from last time, which is the SYZ case, right? So remember, the situation was we have a manifold and its mirror are both fibrations over the same base, where the fibers are both tori. Okay, so what's the B-brane on this side? Well, let's look at a zero brane. That is just a point, and a point is naturally a complex submanifold, so this is naturally a B-brane. And the associated coherent sheaf is just any skyscraper sheaf over this point. So the moduli space of such B-branes is just essentially points on this torus, right? Yeah, that's the moduli space is parameterized by this torus. What about the A-branes? Well, we can show that the dual A-brane to a point, it sends over by SYZ symmetry, it sends over to a brane that wraps around a dual torus. What I mean by that is it's just a brane with support on the dual fiber, right? And luckily, because of our construction for SYZ symmetry, we know that this fiber is Lagrangian, this is a brane. And in fact, when we impose the fact that it has to have a flat U1 connection, that means the moduli space of such branes is actually correspondent to the space of line bundles. Right? So the moduli space of A branes on this side is just the space of line bundles. What this means is, since mirror symmetry exchanges the modular space of B branes with that of A branes, we have this duality between the points on this manifold, the points on this fiber, and the line bundles on the mirror fiber. That is, these are dual varieties, right? This is exactly, we basically recovered the statement that SYZ mirror symmetry has dual fibers. That's pretty cool. So let's specialize this construction to the case we care about for geometric Langlands, which is the Hitchin moduli space. So remember, we have essentially on one side, we have the moduli space corresponding to the Langlands dual group. And let's just treat this in the complex structure where we can think of it as the moduli space of flat bundles. And on the mirror side, we just have the moduli space of Higgs bundles over the normal group instead of the Langlands dual. So what's cool about this is the B model, the category associated to the B model are B branes on this space, which is the derived category of coherent sheaves on this space here. And that's essentially, that's just O modules on that space. And if you remember from the non-abelian Hodge correspondence, right, that this space corresponds exactly to the modular space of local systems. So this category here is almost identical to the category of O modules on the space of local systems. And this was the category that we needed for geometric Langlands. So that's very promising. Now, there's the issue is the dual categories here are different. So first, let's do the mirror symmetry dual category. That gives us A branes on the Higgs moduli space on the normal group G, or the derived category on that guy. In contrast, geometric Langlands says that we should be getting D modules on bundle G. And sort of the relation between these guys is that the moduli space of Higgs bundles, we talked about this last time, the bund G has a smooth component, so the stable part of it, and the cotangent space of that sits densely inside of the moduli space of Higgs bundles. So these are related objects. The question is, like, what's this guy here? How does this correspondence work? And moreover, how does the manifestation we need about sending flat GL bundles to their Hecke eigensheaf, how does that look in the physics correspondence? So you're going to need to talk about line operators. Oh boy. So let's start with the easy one. We're thinking about a Wilson operator. So basically I pick some loop or line L corresponding on my curve C, and it just goes in loop. And I also pick some irreducible representation of my group G. And the Wilson operator is basically to take, you take what's called the path ordered exponential of our connection around the line. That's just fancy physics words for, it's just a holonomy. You parallel transport a given thing around this line, and you see what you get back. And this gives you a nice gauge invariant operator. It's the Wilson operator. It's one of the most fundamental operators you can think of for a gauge theory. Issue is, it's not actually BRST invariant. We have to do a little bit of work, and that work comes in the form of complexifying it. So we replace the connection A with the complexified connection, where what we do is we add to A, as an imaginary component, we add the Higgs field. And if you remember, the Higgs field was basically like a cotangent vector to the modular space of connections. And this invariant that you do get is a BRST invariant Wilson operator. And this is so nice because if you remember, one of the formulations of the Hitchin moduli space was as the space of flat connections, of this flat complexified connections, which means that essentially this Wilson operator is a very good invariant for that sort of thing. Okay, let's move on to the more interesting one. There we go. It's the Hoofed operator. So the Hoofed operator has to do with monopoles. So as a warm-up, we're going to think about basically a U1 monopole with a world line L. What do I mean by a monopole? Well, this is basically the Dirac monopole construction. So if you remember from if you know about gauge theories, an electric field is corresponding to a U1 gauge field. As a U1 gauge theory corresponds to a U1 principal bundle. And the idea with a Dirac monopole is that a magnetic monopole has a non-trivial U1 gauge field around it. That's why you get like that's how you get like the effect of the magnetic charge and everything. It comes from the fact that it makes the bundle non-trivial. So we're in 4-dimensional space here. We have the word line of a monopole. We're going to cut it into slices parallel to this. So we have a 3D slice. And then for each of these 3D slices, what we're going to do is we're going to cut out the point at the center corresponding to the line here. So we're going to get rid of that point. And then the rest of the space just contracts down onto a 2-sphere. And then what we're going to do is we're going to twist that thing on that 2-sphere, right? So this is an example here of twisting, right? So you can see that this kind of corresponds to the U1 action, and it twists around a whole lot. Like the U1 part of it twists a whole 360 degrees as you go around the monopole. So this is an example of a twisted line bundle that you sort of get from this monopole construction. And the Chern class of the twisting, it corresponds physically to basically the magnetic charge of the monopole that you added. And on this twisted bundle, you can consider basically the solution to Yang-Mills equations, and you find that the curvature of any connection you have on these that satisfies the Yang-Mills connections has to have a pole at L. Like this, it's pretty easy to describe logarithmic pole. So that's the Hoofed operator. And now the action of the Hoofed operator in path integral, which is what we care about. This is the interesting part. It doesn't act like the Wilson operator did by just basically adding a factor to the path integral. Instead, it actually modifies the space of fields you're integrating over. Instead of integrating over all connections, we're going to integrate over connections with this sort of prescribed singularity at the monopole location given by twisting this bundle. And because of that, it's called a disorder operator, in contrast to the Wilson operator, which is an order operator. So how does this work for a general group G? What's a Hoofed operator for a general G? Well, basically this construction here, the clearest way to say it is that the different Hoofed operators correspond to different ways of twisting the bundle here. And basically that corresponds to different choices of some holomorphic G bundle on CP1 here. Note holomorphic, this is important, not just a topological bundle. So that the classification of these bundles is much finer because topological G bundles are just classified by pi1 G, but we're in a more interesting case than that. So by theorem of Grothendieck, you can actually classify these as basically by choosing some U1 homomorphism, a homomorphism from U1 into our group. And then we do this U1 monopole here. We twist a U1 guy, and then we pull that back to a twisted G bundle. And that gives us all of the possible homomorphic G bundles on CP1. It's pretty cool. And essentially the action of the Hoofed operator is to make a monopole at a given point P associated to this U1 homomorphism. And our analog of magnetic charge, the thing classifying these two Hoofed operators, is now going to be a homomorphism from U1 to G modulo conjugation, i.e. modulo gauge transformations. Now, let me say a little bit more about what actually the Hoofed operator, the magnetic charges look like. So I just said that they were homomorphisms from U1 to G mod conjugation. Let's do the usual trick of changing it from mod conjugation on G to mod the Weil group on the torus, basically getting rid of as many degrees of freedom as we can. So a homomorphism from U1 to the maximal torus, you can just linearize it, and that gives you a homomorphism from the Lie algebra of U1, which is just R, to the Lie algebra of maximal torus, which is a Cartan subalgebra. Again, mod the Weil group. And by definition, these are just the co-weights over group G. Again, mod the Weil group. And again, by definition of the Langlands dual, which replaces roots with co-roots and weights with co-weights. The co-weights of G are the weights of the Langlands dual, modulo Weil group. And then by the highest representation theorem, highest weight theorem, sorry, basically these are in one-to-one correspondence with irreducible representations of the Langlands dual. So basically, magnetic charges are classified by irreducible representations of the Langlands dual group. In contrast, for Wilson operators, the electric charges, which correspond to different types of Wilson operators, those were automatically characterized by irreducible representations of G. And the action of S duality actually acts to change these line operators together. This is S duality or Montagnol duality or GNO duality or electric magnetic duality. It has many names, but it acts to basically replace these ones with the other. And it replaces the Hoofed operator, which acts by essentially inserting a magnetic particle, with a Wilson operator, which acts by inserting an electric particle. And I thought this was cool because this you can see from this basically why you get the Langlands dual showing up in physics at all. This is where it comes from, this electric magnetic duality. So, okay, we have this S duality on line operators. What do we do with it? Well, let's find how these operators play with respect to the other thing we were talking about, boundary conditions. Let's treat these line operators as functors. So let's consider the case. So we have, again, our 2D surface here with a boundary operator on this side, and we're going to consider a line operator running parallel to the boundary. Now, from a macro scale, these basically look the same. They blurs together. It looks exactly the same as a field theory with a different boundary operator. So in that sense, you can consider the action of a line operator on a line L, this line operator here, you can consider the action as modifying a boundary condition. And in fact, this modification is functorial. So again, we have this category of boundary conditions with this morphism given by point operators. And then we apply L here, and it's the same as somehow it's applying L on this guy here and on this guy here, and then somehow on this morphism between them. And this function is functorial. It preserves associativity and everything. So we can think of line operators as functors on categories. Now, what's really cool is that because of the way that we form these line operators, they're actually commutative, which means that the action of basically the line operator 1 and 2, you can switch their order. Now, this is not clear just from this 2D picture. Like, in normal 2 dimensions, how do you just pass these line operators through each other? Like, at some point they must cross, right? Well, this is the cool thing, because remember, we didn't start with just a 2-dimensional theory. Our 2-dimensional theory is an effective theory for a 4D theory, right? And these line operators that we get here on the 2D theory, they're just shadows. Oops. They're just shadows of different line operators coming from the 4D theory that live in basically not only sigma, but cross this compact Riemann surface C. And in 4 dimensions, you can interchange these however you want. You can easily find a homotopy that basically swaps these 2 line operators. So even though these 2 line operators have the same shadow in the 2-dimensional theory, the true line operators coming from the 4-dimensional theory are different, and you can interchange them. This basically means you can pass them through each other like this. The reason why you're allowed to basically homotope these guys is that the action of homotoping, basically the location of these guys, is effectively the same as the modification of the metric in a way. And again, we've done a twist to make our theory topological. So that doesn't matter up to BRS to exact terms. That's why we can do this. Okay, so commutative line operators are functors. So now let's talk about eigenbranes, right? So they're functors on the category of branes. What about eigenbranes of these functors? So we define a brane B to be an eigenbrane of a line operator if the action of the line operator on B acts by tensoring with some constant vector space V. So what do I mean by tensoring a brane with V? Well, the abstract definition is basically given any other brane, if I look at the homomorphisms, or equivalently, you can think of it as the Hilbert space of strings between these guys. Anyways, homomorphisms from B tilde to B tensor V this is a vector space, and this vector space is equal to the vector space of just B tilde to B, and then that tensor V. But with the geometric sort of notion that there's a much more concrete characterization, right? So let's consider basically Dbrains. So Dbrains, in fact, let's like a submanifold. So a Dbrain corresponds to a submanifold here with some Chan-Payton vector bundle over it. And the action of the tensor product acts solely on the Chan-Payton sheaf. It doesn't affect the submanifold at all. So for example, in this case here, we tensor by C2, and that basically doubles the vector bundle over this submanifold. So in general, you can think of the act of tensoring by some Cn as basically taking n copies of B summed together, n copies of the brane summed together. So that's what an eigenbrane is. Now, what's cool about this is that this notion of eigenbrane plays really nicely with S duality. So imagine that we have basically an eigenbrane of a Wilson operator. Well, let's apply S duality transform. So that sends the brane to the dual brane, and it sends the Wilson operator to the Hoofed operator with the dual representation. And basically, you immediately get that this dual eigenbrane has to be an eigenbrane of the dual operator, and in fact, the eigenvalue is the same. Moreover, as we showed on last slide, line operators all commute with each other in our case, which means that they can have that means that their eigenbranes, they have simultaneous eigenbranes, right? So all Wilson operators have the same eigenbrane, and all Hoofed operators have the same eigenbrane. So let's look at what this eigenbrane is. So for the case of electric eigenbranes, that is eigenbranes of the Wilson operator. Now this is actually this construction is very canonical. It's almost like tautological, like basically the constructions of each of the things are pretty much the only thing you can imagine. But the issue is it's so canonical that I find it very confusing to wrap my head around. And this picture helps me a lot. So it's not just pretty eye candy this time. Anyway, so Wilson operator. So we have a Wilson operator on our two-dimensional manifold running parallel to a boundary. And what we're going to consider is we can treat this operator as coming from a four-dimensional operator by saying that it's a line operator that is constant on the value of on C. It has a constant value P. So we basically have this parameterization by C of different Wilson operators. So again, we choose an irreducible representation and everything. Now, what we're considering for an electric eigenbrane, we're going to show that essentially all zero branes are eigenbranes. So what is a zero brane? A zero brane maps every point on our boundary to the same point on our target space, which in this case is the modular space of flat connections of GL bundles, the modular space of flat GL bundles. Now zero brane here. Now the zero brane, again, it's a point in the modular space of flat GL bundles over C, which means that the zero brane is naturally associated to a flat GL bundle over this guy. And choosing a representation, you can take the associated bundle, and you get this very canonical vector bundle over C. And in particular, you can take the restriction of that vector bundle to the point P, and that just gives you a vector space. Okay. Now, the action of the Wilson operator on the zero brane, it turns out, is just to tensor the Chan-Payton sheaf over the zero brane. That's just a vector space over the zero brane. Just to tensor that with this canonical vector space. That's it. In particular, that means zero branes are eigenbranes. And the eigenvalue corresponds to this vector space here, the one at this point here. And as a more useful notion, we can consider varying the eigenvalue over the whole curve C, and that basically traces out a vector bundle of different eigenvalues. So we can consider, if we drop this P index, we can consider this whole family of Wilson operators, then it has an eigenvalue of just this, basically this canonically associated flat GL bundle. Okay. Now let's talk about magnetic eigenbranes. And I'm actually going to start with going back to Hecky stuff. And I'm going to remind you all what the definition of a Hecky eigensheaf and an eigenvalue is. It's going to be very reminiscent of something. So eigensheaf with an eigenvalue epsilon, it's a D module on bun G. We have the property that if you take a Hecke functor, the Hecke modification, which is parameterized by an irreducible representation of the Langlands dual, oh, that should not be dual, it should just be by an irreducible representation of G, and by a point on a curve C, then its action is just to tensor the D module by this vector space. And in particular, in the same way as on the last slide, these all glue together into what you can consider the full Hecke eigenfunctor on this D module acts tensor by this eigenvalue that is a vector bundle over C. Okay? So this is very reminiscent with the definition of eigenbranes. Now, the definition of the Hecke eigenfunctor, what it does is, at a point P, it increases the degree of these these should be the irreducible representations of the dual. Sorry about that. So anyway, the Hecke eigenfunctor, Hecke eigenfunctor increases the degree by 1 at P of the associated vector bundle. And the way it does that is it does that with the associated, basically, U1 U1 homomorphism into G. So for example, if G is U1, then the Hecke functor of this guy at a point P just acts to increase the degree by essentially adding a divisor at that point. You're allowing poles at that point. This is almost exactly the Hoofed operator, right? Remember this guy over here? Basically what we're saying is we're taking each little sphere around any given point on the baseline, and we're modifying it so that the degree increases by 1 by adding a pole, by adding a singularity by twisting the principal bundle, by adding a magnetic monopole. Right, so we have this correspondence between Hecke eigensheaves on one side and magnetic eigenvalues on the other. Now, it's not quite this cut and dry, because the Hoofed operator actually acts on A branes. It doesn't act on D modules. So to make this precise, we're going to need to how do we find a way to get from an A brane to a D module? Okay, and the way we do that is actually pretty cool. So, right. So we're going to define what's called the canonical coisotropic brane. So first, as an aside, as an important thing, we can think of the homomorphisms from B to B tilde as just a module of homomorphisms from B tilde to B tilde. And that simply means that like this guy acts on this guy, and the action is really simple. This is true for any category. You can do this. Basically, given a homomorphism from B to B tilde, and then one from B tilde to B tilde, by composing them together, you get another homomorphism from B to B tilde. So this acts on this. And the way we draw this in the string case is that we have B tilde here with a point operator here and B here, and then we take this construction I did earlier where we expand this out and get here. And basically the thing we're considering is open string states on this 2 manifold with these boundaries. Okay, so let's define the canonical coisotropic brane. So we want it to be canonical, so let's choose the most canonical coisotropic submanifold we can think of, which is just the whole manifold itself, which is clearly coisotropic because the normal bundle is 0. So I mean, this inflected form has to be 0 and you're strict to there. And it turns out if you impose the A brane condition on it, you have a U1 bundle, and we demand that the curvature of this U1 bundle satisfies that the inverse of omega, inverse of the symplectic form, times the curvature 2 form is an almost complex structure. It squares to -1. Now, the more useful version of this requirement is basically saying that by adding the symplectic form and the curvature form together, the imaginary curvature form together, you can combine them into a holomorphic symplectic form. Okay, so let's consider the case we care about, the moduli space of Higgs bundles, and we're going to consider the A branes of this with the symplectic form omega sub k. Why omega is okay? Well, if you remember from last time, we can basically construct holomorphic symplectic forms from any of the other two. So in fact, we get combining omega k and omega j, we get a holomorphic symplectic form that's holomorphic under complex structure I. And I described this last time. This is just the integral of basically the connection A wedge with the Higgs field, where these are considered as points in the cotangent space of connections. This is the canonical symplectic form associated with a cotangent bundle. This is just dq wedge dp, right? So then what we're going to do is, this was defined for the whole space of fields, the whole affine space, this whole affine space here. So we take the hyperkähler quotient, and to make sure it makes sense, we're going to restrict it specifically the cotangent bundle of the space of stable G bundles, right? So this is a smooth manifold, and this, as we said earlier, this sits densely inside of this guy, inside there, right? So the question is basically, so this is our setup. Now the question is, what is the homomorphisms from the canonical coisotropic brane to itself? Because remember, any string state is just homomorphic, is a module of these guys, right? So let's look at that. And this is actually, yeah, I'm sorry if I can't explain this very loosely, because I don't feel like I understand this extremely well myself. But here's basically the general idea, is that this actually is D modulus, which is exactly what we needed. And the way we get its D modulus, it's really cool. It's because it goes through deformation quantization. So here's kind of how we see it. So remember, our space of fields is essentially, we're restricting the fields that lie in the cotangent space of the space of stable bundles, okay? So A model action, the action of the thing in the A model is, it's 1 over h bar. You can show that it's basically given by omega minus I times the curvature. And this was exactly the holomorph, and then plus B is the exact terms, we can just stick one of those, nobody really cares. And this is exactly the thing we had last time and in the last slide, and this is the holomorphic symplectic form that corresponds to the canonical symplectic form over this cotangent bundle here, dp, which dq. So that means the action is, since this is, in fact, this is an exact symplectic form, and it comes from basically the canonical, the tautological one form, the Louisville one form, if you will. This QDP, which is a one form on any cotangent bundle. You can define it like that. And basically, by doing Stokes' theorem, the integral over the whole 2D thing is just the integral over the boundary of this one form, of this canonical one form. So what this corresponds to actually is that this is the definition of the classical action of a particle moving on the cotangent space of the space of stable bundles, the classical action of a particle along the path of the boundary of sigma. And so basically, when we do the path integral of this guy, that corresponds to the quantization of the classical action of a particle moving along this path. And that's exactly the same as the deformation quantization of this cotangent bundle. So a deformation quantization is basically, I start with a commutative sheaf of algebras of just holomorphic functions where given by multiplication. And then by deformation quantization, what I do is I keep adding terms of order h bar, the first one of which is the Poisson bracket of two of them, and at higher and higher order terms, it gives you what's called the Moyle product. But anyways, the idea is you can think of this as it's a non-commutative algebra, and it's a deformation of the sheaf of algebra. It's a non-commutative deformation of this sheaf of algebras over just over the space here. Now, another trick we can do from quantum is we can consider this as differential operators. So instead of thinking of P as a coordinate, we can think of it as IH bar d dq. right? So basically, and then when we do it this way, basically the commutator of this operator and Q, this gives us basically the canonical commutation relationship that you need for a quantum system, P and Q. And this gives you the deformation quantization. So basically, this non-commutative deformation is in one-to-one correspondence. It is isomorphic to the sheaf of D modules because of this thing here, right? Actually, I need to be a little bit more precise about it. So the homomorphisms of canonical coisotropic brane to itself, once you sheafify it and everything, it gives you a sheaf of differential operators, not actually on just this 1G itself, but actually the square root of the canonical bundle of 1G. This should be 1G. Oops. And the reason for that is basically this is a local construction, and you have to check the cocycle condition of when you have a few of these together. And if you look at the cocycle condition, basically you see that the quantized sheaf has to live on a different line bundle, the square root of the canonical line bundle. But the point of all this is that basically you can easily transfer from this differential operators on this line bundle to just normal D modules, right? So homomorphisms from B to the canonical coisotropic brane of B are modules of this guy correspond to differential operators. So this is the sheaf of D modules, right? And in fact, the eigenbranes of our guy B, right? The eigenbranes with eigenvalue epsilon, they correspond under this correspondence to a D module with Hecke, that is a Hecke eigensheaf with the same eigenvalue. I mean, like, this is easy to say and all, but basically a pretty big portion of the hard work in the Kapustin-Witten paper actually comes down to showing that these things actually correspond to each other and that everything works out nicely. Anyway, this is the main idea. Now, I'm just basically to summarize the whole story that we have, okay? So we're starting with basically a flat GL bundle, flat bundle in the Langlands dual group. Oh no, over a curve C, right? So it's kind of corresponding to this guy here, right? So we use the Hitchin system. We correspond this to a point in the Hitchin moduli space over here. And this is the Hitchin moduli space for Langlands dual group, right? And then what we do is we use S duality, the mirror symmetry of this space, which we showed last week, that sends essentially a point here to a line bundle over the dual torus. And again, it sends the A model. Oh, I mixed these up. That should be B, and that should be A. It sends a B model here over to the A model on this guy. And what's cool is we showed already that this was, we showed pretty easily that this was an electric eigenbrane. It's an eigenbrane of the Wilson operator, right? Because it's a zero brane. And it has the eigenvalue of essentially roughly this guy. And then we map under S duality, which is the same as mirror symmetry. So these all work together nicely. We map under S duality, and we get that the dual brane here that we got from SYZ construction has to be a magnetic eigenbrane with the same eigenvalue. And then with the thing we just talked about, by taking the homomorphisms with the canonical coisotropic brane, what we get is we get actually a D mod for Bungie, and because of this chain here, is actually a Hecke eigensheaf, and it has the right eigenvalue. And basically through this big chain of different physical notions and all of this together, we have manifested geometric Langlands. We have sent a G bundle to a Hecke eigensheaf. And that's what we set out to do. Right? Okay. Yeah, that's pretty much it. That's the idea of the Kapustin-Witten paper in one slide. And that is all I have for today. So if there are any questions. Yeah,
So I have a little question.
Mm-hmm.
So in Kapustin-Witten, they make use of all three complex structures, and they actually talk about BAA branes going over to ABA branes, where the three letters refer to the three.
Right.
Can you say in a word how that fits into?
Basically, I think the way that fits in is this is a hyperkähler manifold, right? So there's three different complex structures, which means that these branes are characterized, as you say, by whether they're symplectic or complex with respect to the given structures. I think ultimately that it's kind of just unnecessary for the limited sort of scope of the application I proposed to consider like all three of the letters, right? Basically, the only letters that we care about are, I guess, the ones corresponding to the case structure, I think, and that's the ones that I described. Hopefully that explains it.
Okay.
Also, I have one more slide just where I can say a few words about different generalizations or extensions of these ideas, but I'm already over time, so I'll do that if there's some interest. But that should take like 5 minutes if I want to go through it. Okay.
Yeah, so sorry, so could I ask a question? So I mean, obviously there's a lot of what you're saying that I'm not really following. That's my fault, but so it seems that this picture that you've drawn definitely seems to explain the case where you have some sort of an irreducible flat LG bundle, and then you're gonna take it through this complicated physics business, and then you end up with the D module, which happens to be the Hecke eigensheaf. So does this physics also explain, I mean, so I wasn't sure if what we were doing, were we just taking a flat LG bundle, or can you run through this thing but just by taking an arbitrary like local system on LG? So does it, in other words, do we really get this geometric Langlands conjecture in the sense when we're thinking about it as an equivalence of categories between the entire, like, you know, all the O modules on the local systems and then all the D modules on Bungee, or does this physics explanation really only apply to the rigidity condition here where we're looking at the flat LG bundles corresponding to Hecke eigensheafs?
So I don't think it applies to the whole categorical equivalence. I mean, mainly because the categorical equivalence, as I laid it out, isn't actually true, as you talked about in your talk. But basically, the main crux of this, basically, to get the categorical equivalence, we only need to use SYZ stuff and homological mirror symmetry. And that basically gives us everything, all of the categorical stuff we need. So all of this extra structure here was basically stuff that I put up to basically affirm the essential property of the categorical equivalence. We can't just have any categorical equivalence. It has to be one that sends flat bundles to Hecke eigensheafs. Right. And basically with all of this other structure, I've shown that the categorical equivalence you get from homological mirror symmetry actually manifests this exactly as we want.
Okay. Okay. Okay, thank you.
Other questions? Okay, if not, why don't we stop the recording?